Hello students, today topic magnetism and matter. So, related to magnetism and matter, the first topic number 1, magnetism. So, what is meant by magnetism? So, the property of a substance by virtue of which the substance can attract other substances like iron, nickel and cobalt is called magnetism. And next, magnets. So, magnets means those substances which are having this property of magnetism are called magnets. So, here in our discussion we are mainly concentrating on two types of magnets, bar magnets and horseshoe magnets. So, here in our discussion we are mainly discussing about bar magnets, next horseshoe magnets. So, these are the two important types of magnets, and when we come to bar magnet, what are the points we have to understand? Now, here we are particularly concentrating on bar magnet. So, regarding the bar magnet, so here a rectangular shaped substance which consists of the property of attracting other substances like iron, nickel and cobalt. So, here this is the shape of the bar magnet, and a bar magnet, it possesses the property of attraction at the two ends of the magnet, and here these ends where the property of magnetism is concentrated, these are called magnetic poles. So, like that what happens to see, every magnet consists of two poles and hence it is called dipole. A bar magnet is also called a dipole like this. So, here one is called south pole and another one is north pole like this. Distance between the two poles is called magnetic length, or we can call it as effective length of the magnet. Effective length of the magnet or magnetic length is represented by the symbol 2L, whereas the physical length of the magnet is called geometric length. So, let us suppose geometric length is equal to L. The physical length of the magnet, it is called geometric length. In general, it is represented by capital L, whereas distance between the two poles of the bar magnet, it is called effective length, or we can call it as magnetic length. It is represented by the symbol 2L. And here some important points related to magnetic length. So, here related to magnetic length 2L, what are the points we have to understand? Number 1, magnetic length is a vector quantity, means which consists of both magnitude and direction. Direction of magnetic length is from south pole to north pole of the magnet. As it is a vector quantity, it consists of direction. The direction of magnetic length is from south pole of the magnet to north pole. And here we can consider magnetic length 2L is equal to 5/6 of the geometric length. Capital L is the geometric length. So, here from the figure we can easily understand magnetic length is slightly less than the total length or geometric length of the magnet, and the relation between magnetic length and geometric length 2L is equal to 5/6 into capital L. Some more important points related to magnetic length. Now, here when we cut a bar magnet parallel to length of the magnet like this. So, when we cut a bar magnet parallel to length, magnetic length does not change. So, magnetic length remains the same. However, the number of the pieces we cut parallel to length of the magnet, for each small piece magnetic length remains the same, whereas when we cut a bar magnet perpendicular to length like this, when we cut a bar magnet perpendicular to length, what happens to see magnetic length changes. And here one more important point related to magnetic length. Whenever a bar magnet is bent like this, then what happens to magnetic length means magnetic length decreases. So, we know that magnetic length means it is the shortest distance between the two poles. So, when we bend a bar magnet like this, distance between the two poles decreases, the two poles come close together. As the two poles come close together, what happens to see distance between the poles decreases and hence magnetic length decreases. So, these are some important points we have to keep in mind related to magnetic length. And after that, just now we came to know that every magnet, it possesses its magnetic property at the ends called magnetic poles, and the strength possessed by each one we can call it as the pole strength. Pole strength is represented by the symbol small m. This is the symbol for the pole strength. Pole strength is represented by the symbol small m. Regarding the pole strength, what are the important points we have to notice? Number one, first one, pole strength is a scalar quantity. It is a scalar quantity which consists of only magnitude and no direction. And after that, the unit of pole strength ampere meter, and here for magnetic length, what is the unit means we can take meters. The unit of magnetic length is meters, whereas the unit of pole strength is ampere meter. Further, this magnetic pole strength small m depends on width of the magnet. It depends on width of the magnet. So, here on the basis of this point, we can say if this is the bar magnet, when we cut a bar magnet into two halves parallel to length, then for each piece pole strength becomes half. If we cut into three equal pieces parallel to length, then for each piece pole strength becomes 1/3. So, here this is how pole strength depends on the width of the magnet. So, therefore, if we cut a bar magnet perpendicular to length like this, however, the number of the pieces we cut perpendicular to length of the magnet, so we can imagine the width of the magnet remains the same. Width remains the same means pole strength remains the same. So, here these are some important points we have to keep in mind related to pole strength. And after that, I am going to introduce you one more important physical quantity called magnetic moment. After that, the next one, magnetic moment. This magnetic moment is represented by the symbol capital M. As it is a vector quantity, we can write it as m bar, magnetic moment. So, related to magnetic moment, some important points. Capital M, magnetic moment capital M, it is a product of pole strength and magnetic length. Small m into 2L, product of pole strength into magnetic length. Next point, as 2L is a vector quantity, capital M is also a vector quantity, and moreover, as magnetic length direction from south pole to north pole, for magnetic moment also, what is the direction means from south pole to north pole. Next, the unit of magnetic moment, just now we came to know that for pole strength ampere meter, 2L means meter, ampere meter into meter, ampere meter square. This is the unit, and further dimensional formula we can write AL square. This is the dimensional formula for magnetic moment. Earlier, for pole strength, we can write the dimensional formula as A into L. Ampere meter Therefore, we can write the dimension formula for pole strength A into L, whereas for magnetic moment the dimension formula A L square. And some more important points related to magnetic moment. So, here when we cut a bar magnet into two equal pieces like that, then what are the changes? So, here one after the other. First, regarding the magnetic length does not change, that means final magnetic length is equal to initial magnetic length. 2L dash means final magnetic length, meaning magnetic length of each piece, and 2L is the initial magnetic length. For each piece magnetic length remains the same, 2L dash is equal to 2L. And next, pole strength M dash is equal to M by 2. Just now we came to know that pole strength depends on width. When the bar magnet is cut into two equal pieces parallel to length, then what happens to see, width becomes half. As width of each piece becomes half, pole strength becomes half. Next, for each piece magnetic moment M dash is equal to M by 2. So, length remains the same, but pole strength becomes half. Therefore, what happens to magnetic moment means M dash is equal to M by 2. Like this we can write. Some more important points here. As a seventh point, look here. When a bar magnet is cut into two equal pieces perpendicular to length, what are the changes, corresponding changes? So, here we can easily understand that when the bar magnet is cut perpendicular to length into two equal pieces, for each piece what happens to see, magnetic length becomes half. Therefore, 2L dash means the length of each piece is equal to 2L by 2, half of the initial magnetic length. Next, pole strength M dash. M dash means pole strength of each piece. You know that in this case width does not change and hence pole strength does not change. Therefore, M dash is equal to M. Next, magnetic moment M dash. Though pole strength remains the same, as magnetic length becomes half, then magnetic moment also becomes half. Therefore, M dash is equal to M by 2. So, this is how we can find the magnetic length, pole strength and magnetic moment of the small piece. And related to this, one more important point. Now, here if a bar magnet is cut into 4 equal pieces like this, 4 equal pieces, 2 parallel to length, 2 perpendicular to length, altogether 4 equal pieces are there, and for each small piece what are the changes. So, here for each small piece we suppose length is 2L dash, 2L is the original length, that means before we cut the magnet, magnetic length is 2L, and after cutting the magnet into 4 equal pieces, for each small piece magnetic length is equal to 2L dash, then 2L dash is equal to 2L by 2, means magnetic length becomes half. And after that, pole strength. So, here we can easily understand, when we cut into 4 equal pieces like this, width of each piece is half of the original magnet. As width becomes half, pole strength also becomes half. Therefore, M dash is equal to M by 2. So, here length becomes half, pole strength becomes half. As both becomes half, then for each small piece magnetic moment M dash is equal to M by 4. Capital M is the original magnetic moment, means before we cut the magnet, magnetic moment is capital M, and after cutting the magnet into 4 equal pieces as shown in the figure. So, for each piece the magnetic moment M dash is equal to how much, means it is M by 4, like this. So, here after that we are discussing about one important area related to magnetic moment. So, that means here when two different bar magnets are arranged in different positions, what will be the resultant magnetic moment, we are discussing about that. So, here related to this different cases. So, here we can take the heading as resultant magnetic moment. Resultant magnetic moment. First case, in the case number 1, we are arranging 2 bar magnets. These are the 2 bar magnets. This is first magnet, this is second magnet. For the first magnet, magnetic moment south to north, this is m1. For the second magnet, magnetic moment south to north, that is also m2. So, like this in the exam, if it is mentioned, 2 bar magnets are kept one over the other, such that south pole on south pole, north pole on north pole, like that, similar poles one over the other. What is the resultant magnetic moment of the combination? So, then here, as both are in the same direction, both the magnetic moments are in the same direction. In this case, the resultant magnetic moment mr is equal to m1 plus m2. So, here this is a vector addition. When theta is equal to 0 degree, then the resultant magnetic moment is calculated to be m1 plus m2. So, in the similar manner, you can understand the next one. So, here in this case, now 2 bar magnets are kept one over the other, like this. This is south pole, this is north pole, this is north pole, this is south pole, and here the magnetic moment m1 from south pole to north pole means it is towards right, and for the bottom magnet, magnetic moment south to north means this is m2. So, here in this case, the 2 magnetic moments are in opposite direction. As the 2 magnetic moments are in opposite direction, the resultant magnetic moment is calculated to be mr is equal to m1 minus m2. This is how the resultant magnetic moment mr is equal to m1 minus m2, like this. This is the second case, and after that, third case. Regarding the third case, here 2 bar magnets are arranged like this, side by side. Earlier one over the other, now side by side. This is south pole, this is north pole for the first magnet, this is south pole and this is north pole for the second magnet. For the first magnet, magnetic moment south to north, its magnetic moment is m1. For the second one, magnetic moment is from south to north, let us suppose its magnetic moment is m2. So, in this arrangement means tomorrow in the exam, so it may be described like this, the figure can be described like this. How? 2 bar magnets are kept side by side such that unlike poles are in contact. That means north pole of one magnet is kept in contact with the south pole of the other, both are kept side by side. What is the resultant magnetic moment in this case? Then the resultant magnetic moment mr, it is calculated to be m1 plus m2. This is how the resultant magnetic moment m1 plus m2. And here similarly, if 2 bar magnets are kept side by side, this is south pole, this is north pole, this is north pole, this is south pole. There are 2 bar magnets, they are arranged side by side such that like poles are in contact, north and north both are in contact. So, in this case, we suppose for the first magnet, magnetic moment m1, it is south to north means it is towards right. For the second magnet, magnetic moment south to north means it is left side, its magnetic moment is m2. For the first one, magnetic moment m1 is towards right. For the second one, the magnetic moment m2 is towards left. Both are in opposite direction. Magnetic moment is a vector quantity. When 2 vector quantities are in opposite direction, then resultant magnetic moment Mr is equal to M1 minus M2, like this. This is how we can find out the resultant magnetic moment. And after that, some more important points. 4 cases completed. Now case number 5, fifth case. Let us suppose there are 2 bar magnets. This is the first one and here this is the second magnet. Both are kept like this. Say here for the first one this is south pole and this is north pole. For the second one this is south pole and this is north pole. Let us suppose angle between these 2 magnets is theta. For the first magnet, magnetic moment from south to north, let it be M1. For the second magnet, magnetic moment south to north, let it be M2. So, this is how when we arrange 2 bar magnets at an angle theta such that the angle between magnetic moments M1 and M2 is equal to theta, then the resultant magnetic moment Mr, it is calculated to be under root M1 square plus M2 square plus 2 M1 M2 cos theta. Like this, we can calculate the resultant magnetic moment of 2 bar magnets for this arrangement. And after that, when 2 bar magnets are arranged like this, means in the form of plus shape like this. This is south pole, this is north pole, this is south pole, this is north pole. For first magnet, magnetic moment is south to north, let it be M1, let it be M1. And for the second one, magnetic moment, it is upward south to north, let it be M2. So, like this here, the 2 bar magnets are arranged like this. We can understand the angle between the 2 magnetic moments 90 degrees. In this case, the resultant magnetic moment Mr is equal to under root M1 square plus M2 square. This is how we can calculate the resultant magnetic moment when 2 bar magnets are arranged in the form of plus shape. Similarly, here even if 2 bar magnets are arranged in the form of L shape like this here. So, L shape, say here this is south, this is north, this is south, this is north, angle between them 90 degrees. If 2 bar magnets are arranged like this, what happens to see? In this case also you can easily understand the resultant magnetic moment will be same. So, here this is the magnetic moment of the first magnet south to north, and here this is the magnetic moment of the second one south to north vertically up, and here south to north towards right, angle between them 90 degrees. Then the resultant magnetic moment Mr, it is calculated to be under root M1 square plus M2 square. This is how we can calculate the resultant magnetic moment if 2 bar magnets are perpendicular to each other. And after that, some more important points related to this. As 8th one, look here, if 3 identical bar magnets are arranged like this. So, here all are identical magnets by all sense, by all means. Look here, the 3 magnets are identical, that means pole strength, length, magnetic moment, everything is same for the 3 magnets. So, here they are arranged such that this is south, this is north, and here this is south, this is north, and after that this is south, this is north, like this. Here the magnets are arranged like this, each of length 2L, say each of length 2L, and each of magnetic moment capital M. each of magnetic moment capital M. So, this is a very standard arrangement, examination point of view, very important case. So, this is how when three identical bar magnets are arranged in the form of an equilateral triangle such that unlike poles are in contact at each and every corner, then in this case the resultant magnetic moment Mr, it is calculated to be 0. The resultant magnetic moment is calculated to be 0. How it is 0? So, we can discuss shortly, but this is the standard result, and here we can prove by using the knowledge of vectors, we can prove that resultant magnetic moment is equal to 0. Similarly, here one more of this kind, if 4 identical bar magnets, this is how 4 identical bar magnets, by all means these are identical, 4 magnets altogether, they are arranged in the form of a square such that, like earlier, here also if this is south north, this is south north, this is south north, this is also south north. So, here all the 4 identical bar magnets are arranged in the form of a square such that unlike poles are in contact at each and every corner, south north, south north, south north, south north, like that, unlike poles are in contact. So, here also the resultant magnetic moment Mr is equal to how much, means it is 0. The resultant magnetic moment Mr is calculated to be how much, means it is 0, like this. And here after that some more important points related to magnetic moment. Let us consider here this is one bar magnet, its magnetic moment is M. For a bar magnet, magnetic moment is M. So, in the problem if it is mentioned the bar magnet is bent in the form of arc of a circle, like this, it is bent in the form of arc of a circle such that it subtends an angle theta at the center. The same bar magnet, it is bent in the form of arc of a circle such that it subtends an angle theta at the center. Now, what happens to resultant magnetic moment? Every student, you can understand, when we bend the bar magnet, the two poles come close together, magnetic length decreases, magnetic moment decreases, pole strength remains the same. So, here the decrease in magnetic moment is on account of decrease in length of the bar magnet, but pole strength remains the same. We are not changing width of the magnet, width remains the same, means pole strength remains the same. So, here on simplification, in this case the resultant magnetic moment Mr is calculated to be 2m sin theta by 2 whole divided by theta. This is the formula for the resultant magnetic moment, very important formula for examination point of view. So, 2m sin theta by 2 divided by theta, and one more thing, you know that here whenever we take theta separately, then theta should be always in radian. So, in the denominator that theta should be always in radian, means tomorrow in the problem if it is mentioned the bar magnet is bent in the form of a semicircle mentioned, say theta means pi, we have to substitute. In the form of here it is mentioned quadrant of a circle mentioned, theta is equal to 90 degrees, like that. Look here, 90 degrees means it is pi by 2, 180 degrees means it is pi, 90 degrees means pi by 2, 45 degrees pi by 4, 60 degrees pi by 3, 30 degrees pi by 6. These are the this is how we can convert degrees into radian, and here in the formula theta should be always in radian. And related to this most common question, when a bar magnet is bent in the form of a semicircle, what will be the final magnetic moment? That is the most standard question here. As 11th one, in the problem if it is mentioned the bar magnet is bent like this in the form of a semicircle, before we bend the magnet, magnetic moment is m, say, that is initial magnetic moment. When the magnet is straight, magnetic moment is m. Now, the magnet is bent in the form of a semicircle, what will be the final magnetic moment? So, here in this case m dash is equal to 2m into sin theta by 2, theta 180, 180 by 2 means sin 90, sin 91 divided by in the denominator theta. So, in this case when it is bent in the form of a semicircle, theta is equal to pi radian. Therefore, when it is bent in the form of a semicircle, m dash is equal to 2m by pi. This is a standard result, m dash is equal to 2m by pi. So, very often in the exam the same result, look here they use it to mention like this 7m by 11. So, in a generally in the competitive exams they use it to mention this answer 2m by pi as a 7m by 11. Pi can be written as a 22 by 7. When you write pi is equal to 22 by 7, 7 goes to numerator, 2 cancels in 22 by 11 times. Therefore, we can write it as a 7m by 11 like this. So, here some more important points of this kind. Tomorrow in the problem if it is mentioned, this is one bar magnet, its magnetic moment is capital M. Now, the bar magnet is bent in the form of a regular U shape, like that they will mention. The bar magnet is bent in the form of a regular U shape. Regular U shape means all the arms are of the same length. All the arms are of the same length means here this becomes 1/3 of the initial length, this becomes 1/3 of the initial length, this becomes 1/3 of the initial length. Initial length is equal to 2L, say. Before we bend the magnet, initial length is equal to 2L, initial magnetic moment is equal to M. When we bend the magnet in the form of regular U shape, the length of each arm is equal to 2L by 3. So, from this we can understand the distance between the two poles, say this is south pole and here this is north pole, and this length is equal to how much means that is 2L by 3. Distance between the two poles is called magnetic length. Now, the magnetic length becomes 1/3. As magnetic length becomes 1/3, magnetic moment also becomes 1/3. So, therefore, in this case what is the final magnetic moment? M dash is equal to how much means M dash is equal to M by 3 like this. This is how we can solve the problems. And related to this there is another important examination point of view, one more important case is there. What is that? In the problem it will be mentioned there is one bar magnet, its length is 2L, its magnetic moment is M. This is initial case. The bar magnet is, look here it is straight, its magnetic length is 2L, magnetic moment is M. In the problem it will be mentioned the bar magnet is bent in the form of a regular S shape. In the problem it will be mentioned the bar magnet is bent in the form of regular S shape. So, regular S shape meaning, so here all the arms are of the same length. Totally how many parts are there? 5 parts. So, this is 1, 2, 3, 4, 5, 5 parts are there. So, each part becomes 1/5 of original one, 2L by 5, this is 2L by 5 and this is also 2L by 5. Now, say this is south pole and here this is north pole. This is the new magnetic length, that is the new magnetic length. So, here by using the knowledge of Pythagoras theorem, the new magnetic length south to north you can easily calculate. It is not the difficult thing, you can easily calculate the distance between south pole and north pole by using Pythagoras theorem. One side is 2L by 5, other side 2L by 5 plus 2L by 5, 2L by 5 plus 2L by 5, that means 2 into 2L by 5, this is 2L by 5, this is 2 into 2L by 5, hypotenuse you can calculate. So, here after simplification the final length it is 2L by root 5 you will get. After simplification the final length from south to north pole it is calculated to be 2L by root 5. Pole strength remains the same. So, therefore, the new magnetic moment M dash is equal to M divided by root 5. This is the new magnetic moment. So, this is how we can solve the problems related to magnetic moment and some more important points related to magnetic moment. So, keep concentrating here. Some more important points. What are they? Now, earlier we have discussed about the arrangement of three identical bar magnets. In earlier case, we have discussed all the identical magnets, each of magnetic moment m and having the same length are arranged in the form of an equilateral triangle with unlike poles in contact at every corner. Resultant magnetic moment is equal to 0, and here how it is 0 we are discussing. Look here. So, let us suppose this is south pole, this is north pole, this is south pole, this is north pole, this is south pole and this is north pole, all are identical. This magnetic moment capital M, this magnetic moment capital M and this magnetic moment capital M. So, one thing, by using the knowledge of vectors, if a number of vectors having same magnitude are arranged in the form of a closed polygon, all are of the same magnitude, arranged in the form of a closed polygon, then the resultant is equal to 0. That is most important thing you have to keep in mind. So, tomorrow they may mention 10 identical bar magnets are arranged in the form of 10 sides of a closed polygon, then the resultant is equal to how much, means it is 0. Now, in this case how we can prove that the resultant is equal to 0? The method is most important, that is why we are discussing about that. So, here in order to find out a resultant, what is the procedure? The procedure is like this: we have to arrange all those vectors, means all those magnetic moments from a common point, preferably origin, in the same direction as mentioned in the problem. After that, we have to resolve all the vectors into x components and y components. We have to sum up x components, let it be sigma x. We have to sum up y components, let it be sigma y. Then the resultant can be calculated by using the formula under root sigma x square plus sigma y square. Sigma x means sum of the x components, sigma y means sum of the y components. Then the resultant can be calculated by using the formula r is equal to under root sigma x square plus sigma y square. Like that we can calculate. If you take the first one, here this is capital M, magnetic moment M, and here this is a second one. Like this we can arrange. This is capital M, and this angle with the horizontal 60 degrees, you can take this angle 60 degrees, and this is capital M, like this. This is capital M, and this angle 60 degrees with horizontal. So, this with horizontal this angle is equal to 60 degrees. So, now we have to arrange like this. Try for this problem here in this meantime. So, I hope you are thinking about how to resolve this into vectors. So, first of all, x components, y components, we have to resolve all the vectors into components, x component and y component. If you take this one, x component is m, y component is 0. For this one, x component minus m cos 60, minus m cos 60 means minus m by 2, minus m by 2. And for this one, x component minus m cos 60 means minus m by 2. And for this one, y component plus m sin 60, plus m sin 60 means it is m into root 3 by 2, m into root 3 by 2. And next, for this one, minus m sin 60 minus m into root 3 by 2, minus m into root 3 by 2. So, this is how we can resolve all the vectors into components. Next, we have to sum up all the x components, let it be sigma x. So, here next we have to sum up all the y components, let it be sigma y. Then the resultant r is given by r is equal to under root sigma x square plus sigma y square. This is how we can calculate the resultant, r is equal to under root sigma x square plus sigma y square. When you sum up minus m by 2 means minus m plus m, sigma x is equal to 0. So, here this is root 3 m by 2 minus root 3 m by 2, therefore, sigma y is equal to 0. So, here in this case sigma x is equal to 0, sigma y is equal to 0, then the resultant magnetic moment is calculated to be 0. This is a procedure, and for practice purpose one more problem we are going to do. Again we are considering the same three identical bar magnets, the same three identical bar magnets. So, here this is of magnetic moment m, this is south, this is north, and here this is north, this is south, that is the change. Again this is south, this is north. So, this is how what happens to see the difference between earlier arrangement and the present arrangement. In the earlier arrangement, at every corner unlike poles are in contact, but here it is not like that. At only one corner unlike poles are in contact, here similar poles are in contact, here similar poles are in contact, only at one corner unlike poles are in contact, that is the difference. And here just like earlier, here also all the three magnets are identical and arranged in the form of equilateral triangle. What is the resultant magnetic moment? How to calculate? So, now this is m and here this is m and this is m like this. So, these are the magnetic moments. I hope you remember first step, step number 1, we have to arrange all these vectors from a common point, preferably from origin. From origin we have to represent all the vector quantities. This is first one, capital M, and this is second one like this here with horizontal this angle 60 degrees, this angle 60 degrees, this is M, and here this is M like this, this is M. As it is equilateral triangle, this angle 60 means with horizontal angle 60, with horizontal angle 60. Now, we have to find out the resultant magnetic moment. You know the procedure very well. We have to find out components, x component and y component for all the three vectors, x component and y component. Come to x component. For this one, x component means m, y component 0. For this one, x component plus m cos 60 plus m cos 60 means plus m by 2. Y component minus m sin 60, minus m sin 60 means minus root 3 m by 2, minus root 3 m by 2. This is completed. Next this one, x component minus m cos 60 means minus m by 2, minus m cos 60, minus m cos 60 means minus m by 2, and y component minus m sin 60, minus m sin 60 means minus, here this is the y component, minus root 3 m by 2, minus root 3 m by 2. So, here we have to sum up. Let us suppose sum of the x component sigma x, sum of the y components is sigma y. We have to calculate sigma x and sigma y. Plus m by 2 minus m by 2 cancel. Sigma x means m and sigma y. This is minus root 3 m by 2. This is minus root 3 m by 2. So, therefore, resultant minus root 3 m, minus root 3 m. So, sigma x is m, sigma y is minus root 3 m, and we have to calculate resultant. Resultant formula you know, under root sigma x square plus sigma y square under root sigma x square plus sigma y square. Now, here on simplification r is equal to sigma x square means m square under root m square, sigma y square means minus root 3 m square, that is 3 m square, 3 m square plus m square 4 m square, 4 m square under root, 4 m square under root means a resultant magnetic moment 2 m. So, in this case the resultant magnetic moment r is equal to how much, means it is 2 m. Okay. So, problems of this kind very important. So, in order to solve problems of this kind, knowledge of vectors most important. Okay. And here after this we are going to discuss about next concept, that is Coulomb's inverse square law. Next concept, Coulomb's inverse square law. So, this is related to force between two magnetic poles. Let us suppose there are two magnetic poles. So, let us suppose here this is a south pole and this is also south pole. For this one pole strength is m1 and for this one pole strength is m2. The two poles are separated by a distance smaller, distance between the two poles it is smaller. So, first of all, according to Coulomb's inverse square law, it says that like poles repel each other, unlike poles attract each other. That means, in between south pole and south pole there exists a force of repulsion. In between north and north also there exists a force of repulsion, whereas south and north they attract each other. So, the statement like poles repel each other, unlike poles attract each other. And here regarding the force of attraction or repulsion, the scientist Newton, he had given a law called Coulomb's inverse square law. According to this Coulomb's inverse square law, the force of attraction or repulsion between two magnetic poles is directly proportional to product of the pole strengths. It is directly proportional to product of the pole strengths, F directly proportional to m1 m2, and next F proportional to 1 by r square means inversely proportional to square of distance between the two magnetic poles, inversely proportional to square of the distance between the two magnetic poles. So, here these are the two things given according to Coulomb's inverse square law, and here combining these two we can write F is equal to a constant mu naught by 4 pi into m1 m2 divided by r square. So, here this is the force between two magnetic poles kept in air or vacuum. So, when the two magnetic poles are kept in air or vacuum, the force between the magnetic poles generally represented by the symbol F naught, F suffix naught, that is the force between two magnetic poles kept in air or vacuum, and here the proportionality constant is mu naught by 4 pi. This mu naught is called magnetic permeability, mu naught, it is called magnetic permeability of free space. Magnetic permeability of free space, mu naught, and here mu naught is a constant, its value 4 pi into 10 power minus 7 Henry per meter. The unit of mu naught is Henry per meter, and mu naught value 4 pi into 10 power minus 7 Henry per meter. So, this is the force between two magnetic poles kept in air or vacuum. If the two poles are kept in any another medium, then force is given by the formula F is equal to mu by 4 pi into m1 m2 divided by r square. This is the formula for force between the two magnetic poles kept in some medium. So, here mu is magnetic permeability of that medium, like that. So, here now here you should understand one more important term, this mu divided by mu naught, it is called relative permeability, it is represented by the symbol mu r. So, mu r means it is called relative permeability, mu r is equal to mu by mu naught, mu means magnetic permeability of the medium, mu naught means magnetic permeability of the free space, and from the formula we can say mu r, it is not having units and dimensions, like that. So, it is a pure constant. So, this is about Coulomb's inverse square law, and regarding the magnetic force, it is a central force, it always acts look here along the line joining the two poles of the two magnetic poles, okay, and it is a central force, and magnetic force is the conservative force. Magnetic force is conservative force means work done is independent of the path, it just depends on initial and final positions, but independent of the path. And after that we have to discuss about another important term, that is magnetic field. Magnetic field. So, what is meant by magnetic field? Let us consider a magnetic pole of pole strength, and here the region, the space or region around this magnetic pole, the space or region around this magnetic pole where the influence of this magnetic pole is felt, that region we can call it as a magnetic field. Means if you keep one more magnetic pole somewhere here, let us suppose its pole strength is m1, then this pole of pole strength m1, it will be influenced by this pole of pole strength m. Whereas, if you keep another magnetic pole somewhere here, let it be m2, its pole strength is equal to m2, then this pole cannot influence that one. It can influence the poles which are present within this region. This region where influence of this magnetic pole is felt, it is called as a magnetic field. Regarding the magnetic field, so we can classify into two types, uniform magnetic field and non-uniform magnetic field. Uniform magnetic field means the magnetic field within which strength of the field is the same at every point, both in magnitude and direction. So, at every point within the magnetic field, if the strength is same both in magnitude and direction, such a magnetic field is called uniform magnetic field. The best example for uniform magnetic field, earth magnetic field in a small region. So, here regarding the earth magnetic field, so here when we consider a large area, from point to point the magnetic field of earth changes. But however, in a small region like in a classroom or within a city, the strength of the earth magnetic field is same both in magnitude and direction, and hence that is the best example for uniform magnetic field. So, once again here the best example for uniform magnetic field, earth magnetic field in a small region. Next, non-uniform magnetic field definition. Non-uniform magnetic field means the magnetic field within which strength of the field is different at different points, either in magnitude or in direction or in both, then it is called as the non-uniform magnetic field. The best example for non-uniform magnetic field due to a monopole. So, here let us consider this is a monopole. We imagine, you know that monopoles are imaginary, they do not exist really, just they are imaginary. In order to get a monopole, when you cut a bar magnet into a number of the pieces, however the small pieces you cut, each small piece consists of again south pole and north pole. That means both the poles exist together, south and north exist together. Then when we can imagine monopole, under what condition we can imagine monopole means when a magnet is very long, so then what happens to see, we can consider the two poles as monopoles when it is kept vertically. So, bottom one is south pole, upper one is north pole, say upper one is north pole. This is a very long bar magnet, In the case of a very long bar magnet, we can suppose the two poles are here separate poles, monopoles we can imagine. So, here if you imagine a monopole here, and due to this the magnetic field, it is non-uniform magnetic field. Why? Because it is different both in magnitude and direction. For example, here if I consider 2 points, one point is A, one point is B, one point A. A is very close to the magnetic pole of pole strength M, B is much away, and just with our general knowledge we can say the influence is more at A than at B. That means the strength is more at A than at B. That means from point to point strength of the field due to pole of pole strength M changes in magnitude. Similarly, here what happens with respect to direction also it changes. And here the direction of the magnetic field. How to decide direction of the magnetic field? Wherever we have to know direction of the magnetic field, we have to imagine one north pole at that point. The direction along which north pole travels, that represent direction of the magnetic field. So, this is one important point. All the students look here once again here, how to decide the direction of the magnetic field in any region. In order to decide, in order to know direction of the magnetic field at any point in the magnetic field, there we have to imagine one north pole. In whatever the direction north pole travels, that direction represents direction of the magnetic field at that point. So, here let us suppose this is south pole, say this is south pole, and if you want to know direction of the magnetic field here at this point, say point C, there you have to imagine one north pole. When you imagine one north pole, we know that north pole will be attracted by the south pole. So, this is the direction how the north pole travels. Therefore, this represents direction of the magnetic field, and the strength of the magnetic field we can call it as magnetic field induction. Magnetic field induction is represented by the symbol capital B. Capital B means it is magnetic field induction, and here it represents strength of the magnetic field. Now, we are going to discuss about the definition for capital B, magnetic field induction definition we are going to discuss. So, here with the help of this formula we can define magnetic field induction. So, now the definition, look at the definition. The force experienced by a magnetic pole of unit pole strength kept at any point in the magnetic field is called magnetic induction at that point, magnetic induction at that point. So, once again look at the definition, magnetic field induction. The force experienced by an unit north pole kept at any point in the magnetic field is called magnetic field induction at that point. So, by definition we can write B is equal to F by M. On the basis of this, here we can write the unit Newton per ampere meter, Newton per ampere meter. Force unit is Newton, pole strength unit is ampere meter, the unit of magnetic induction Newton per ampere meter. This is the definition for the magnetic field induction. And here after the magnetic field induction, we have to discuss about formulae for magnetic induction. Magnetic induction due to monopole and magnetic induction due to dipole we have to discuss. So, in the next class we are discussing about magnetic field induction, formulae due to magnetic field induction, and that is it for today. Thank you.